Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, count square submatrices with all ones. So suppose we're given a binary matrix that looks like this, zeros and ones. We want to count the number of square submatrices. So a square is like this is 1 by 1, this is 2 by 2, this is 3 by 3. We have a bunch of like 1 by 1 squares, and we have a bunch of 2 by 2 squares like that. And here as well, it looks like we have about two 3 by 3 squares. So among all of those squares, we want to determine how many of them have all ones. Now, a possible brute force approach, how would you even break down the problem to do it in such a brute force way? Well, kind of what I just showed you. Just create every single square. Well, how do you create every single square? Well, possibly by considering, let's say, each element the top left of the square. So this is the only 1 by 1 square that we can make starting from here as the top left. But we can create a 2 by 2 square where this guy is also the top left. And we can create a 3 by 3 square where this guy is also the top left. And we can kind of repeat that for every single one. Now, for some of these, like this one, we have a 1 by 1, but we can't really create a 2 by 2. So that's something you'll need to handle. Now, for all the squares, though, we just want to confirm that they have all ones. And now if they do, you can take the result and increment it by 1. And keeping track of the total, you can then return the total. So it is possible, theoretically, to do this in a brute force way. But is there a way to do it more efficiently? Is there any repeated work that we can eliminate? Well, when you look at it from here, like let's say this is the top left, we can create the 1 by 1, we can create the 2 by 2, and we can create the 3 by 3. By checking all of these, we're doing a lot of work. We're doing that 1 by 1 matrix, the 2 by 2, and then the 3 by 3. So cells are going to be visited multiple times because then when we're done there, we might ask the same question from here, and we might ask the same question from here, and then end up visiting all of these. There is a pattern. I'll admit it's not trivial to notice the pattern, but in terms of subproblems, if we want to know, can we form a 3 by 3 square from here? How can we figure that out? Well, if you can form a 2 by 2 square from here, the position below it, then that would look like this. I guess I'll make it a different color just to make this very, very obvious. So there's 1. And if you could create a 2 by 2 square looking at the right, you'd get something like this. Now, is that enough information to confirm that we can create a 3 by 3 from here? No, we're missing this guy. Well, we can also go diagonally and then from here, check if the 2 by 2 where that guy is the top left also exists, and then we pretty much have everything covered. So this is how you break this problem down into subproblems. Now you might be thinking, wow, you must be a genius for coming up with that. And you're right, it is a very clever approach, though I don't think it's like impossible to come up with this by yourself. The reason I was able to do it so quickly is actually because I have solved a very similar problem to this one before. It's Leetcode 221. You can see I made that video like 3 years ago. And I will say that that problem is nearly identical to this one that we are solving today. So if you want to practice a similar problem, check that one out. But back to this problem. So knowing that that's how we're going to break this up into subproblems, how do we solve the problem then? Well, the question we want to ask is for every single one of these values in the grid, every single one of these positions, we want to consider it to be the top left. We want to count how many squares we could create from this position being the top left. So how do you do that? How does the subproblem I just mentioned help us do that? Well, think of it this way. We might be able to create a 1 by 1 from here, and we might also be able to create a 2 by 2, and we might also be able to create a 3 by 3. All we really need to know is what is the maximal square, literally the name of that other Leetcode problem I just mentioned. What's the maximal square we could create from this as the top left coordinate? Because once we know that, let's say the maximal square is 3 by 3. Well, if we can create a 3 by 3 with this guy as the top left, where all of these are 1s, then for sure we can create a 2 by 2, and we can also create a 1 by 1. So that's kind of another way of thinking about like the subproblem. A 3 by 3, the subproblem of that is the 2 by 2, and a subproblem of that is the 1 by 1. So how do we figure out the maximal square that we can create given this as the top left coordinate? Well, this is where the recursive part comes up. We could ask the question, what's the biggest square I could create from the bottom position? Same thing with the right position, and same thing with the diagonal position. Suppose from here, it's a 1, right? Like that's the biggest we could create from here. But how would we know that that's the biggest we could create from here? Well, recursively, we're going to ask the same question from here. What's the maximal square we could create from here? We're going to ask the question, go down right, and go to the right. Okay, from here, what's the maximal square? Probably 0, we're out of bounds. What's the maximal square over here? Probably 0, we're out of bounds. What about to the right? Well, here again, recursively, we're gonna look down, diagonal, and to the right, and we're gonna end up in the same case where 0 here, but we go to the right. And then from here, this is probably like the main base case where we're at the bottom right. We look down, diagonal to the right. They're all zeros. Okay, so all the neighbors, the maximal square from all of them, they're all zeros. So what's the maximal square we could create from here? Well, it's just 1. Now that we know that, we can answer the question from over here. Down is 0, down right is 0, but to my right, it's a 1. So what should we do? Among these 3 values that we have here, what do we want from them? We want the minimum among all of those values because that's the bottleneck. If we have a 1 like below it and a 1 over here, but if we have a 0 over here, we can't create the 2 by 2. So that's why we want to collect the minimum of all of these. And so in this case, it's a 0. So we take 0 plus 1 and say that that's the length of our square, the maximal square we can create from here. That's the size, and it's of length 1. Okay, now we answer the question for this guy, and it's the same thing. The biggest we can create here is a 1, here is a 1, and here is a 1. So now, among all of those 3, the minimum is 1, and we take that and add it to the value over here, which gives us the 2 by 2. That's the biggest square we could create from here. Since it's a 2 by 2, there are 2 squares we can create where this is the top left, so we would add to our result 2. As I was doing that, you might have noticed that when I went down from here, I also made a recursive call to the right, but then I went back up here, and then I went diagonally and made the recursive call here. So clearly that's repeated work, and we can cache the results of that repeated work so that we can optimize this solution. Thus, from every single position, we're only going to ask the question a single time. So we can solve this problem recursively with memoization with n times m time, where that is the dimensions of this grid. Now, it's important to mention, imagine that instead of this guy being a 1, it was actually a 0. What's the biggest square we could create where this is the top left? Well, at this point, we don't even need to go recursively because it's a 0. So the biggest square from here is going to be 0. And so the result will not change. Very quickly, the 3 by 3 case, you can imagine from here, we'd go down, and eventually like this would return 2. We go to the right, this would return 2, and then we go over here, this would also return 2. So all of those return 2, so we'd say 1 plus 2. The size from here is going to be 3, so you can see that the math will work out. Imagine though, here, if we had had a 0, we would have gotten a 2 here, and a 2 here, and from here, we would have not gotten a 2, but we would have gotten a 1. So among those 3, the minimum would have been 1, and so that tells us that the biggest square we can create from here would have been the 2 by 2 if this was a 0. So everything works out very cleanly. Let's code it up. So first I'm just going to get the dimensions of this grid. I like to do that like this, putting it into rows and columns, some descriptive variable names. And then I'm going to create that recursive function. I'll call it DFS. I'll pass in 2 variables for the coordinate that we are currently at, the row column. And so I'll immediately just fill in the base case because it's so easy. If we go out of bounds, return 0. So if row is equal to the number of rows, we went out of bounds in that direction, or we could have gone out of bounds in the other direction. Either case, return 0. The largest square we can create out of bounds is of size 0. How exactly do we want to call this recursive function? Because think of it this way. What if we do this? We call DFS on 0, 0. We assume that that's going to handle the entire result and we can just return it. There is actually a problem, at least the way I'm going to code this up, where we want to eliminate all of the repeated work. The issue is if our grid is something like this, let's say 0, 1, 1, and then let's say the rest of them are all 1s. Well, if we started from here it's a 0. So we're going to say that the largest square we can create starting from this coordinate is of size 0, and we're not going to make the recursive call down here, here, or here. Anytime we reach a 0, that's a base case. We can kind of just immediately return. So in other words, I'm going to add that to my base case up here. I'm going to say, or not matrix of the current position. If it's a 0, then immediately return 0. There's nothing else for us to do. So knowing that, we can see how this DFS is going to underestimate the number of squares that we have. Because anytime we reach a 0, even if this one was a 1, maybe this is a 0. Well, from here, we're never going to end up counting this square because we're going to try to go right and we're going to see this is 0 and we're going to terminate. So the way to correct that is to run the DFS for every single coordinate. So for R in range rows, for column in range columns. And then we run DFS, it'll return the count from that coordinate. I'll pass that in like this, and we can take that and add it to our result, which I will declare up here, and then I'll return it down here. This will still be efficient because we will make sure that we never solve the same subproblem more than once. We will add caching to this at the end. So now we can actually try to do the implementation. It's not super crazy. We know there's going to be 3 recursive cases, well, 3 recursive branches. What we want to do is say that the size, or let's say the length of the current square is going to be 1, because we know for sure that the value at the current coordinate is a 1, because if it wasn't, we would have returned here. So we can say it's at least 1 plus the minimum of the 3 neighbors. So DFS on row plus 1, where the column stays the same, DFS on column plus 1, where the row stays the same, and the diagonal as well. So like this. And we take the minimum of them, add that here, and then we get the length of the current square. We want to take that and add it to our result, so we can just return it from here just like that. So we're done with the brute force approach. This is not going to be super efficient, but it's not too difficult to add caching to this. I will declare a hash map up here as the cache, and then here I'll say if these coordinates are in the cache, we've solved the subproblem before, so return the value that has been cached. Now for us to actually add the value to the cache, once we compute it, I will replace the length with this so that we cache the result and then we return the result. So I believe this is the whole code. Let's run it. And you can see that this works and it is very efficient. Now, very quickly, let me show you the bottom-up approach. We can solve this problem without recursion by solving the subproblems in a very particular order. Let me show you. Let's say that this is like the input grid that we're given, and this is like the cache, kind of like in the recursive solution. We saw that what the cache is essentially doing is it's like saying recursively, okay, we want to know the result of this subproblem. Well, like how many squares can we have from here, the largest square from this position. And to do that, we need to figure out the result from here, here, and here. And then from each of those, they're going to make recursive calls as well, assuming that those values are 1. Because if they're 0, well, we're just going to return 0 up to the parent. You can see how that's going to work. This is going to end up being computed first. In this case, that'll be a 1. And then we will do this one. We'll look down here and there. And then this one will end up being a 1 as well. If we wanted to, we could code up a bottom-up approach, which will fill in this grid from the bottom right all the way up until the top left. And that's assuming that for every position, we are saying, if this guy was the top left of the square, what's the maximal square we could make? It's actually possible to solve this problem by taking this grid and not populating it from the bottom, but actually populating it from the top to the bottom right. But for us to do that correctly, we have to invert the way we've been thinking about this problem. Rather than saying this is the top left, let's actually say that this is the bottom right of the square. The reason we have to do that is because if we were saying this is the top left and we're trying to populate that position, we can't possibly populate it without knowing what came to the bottom and to the right of that value. But if we say that this is the bottom right, well, all we would need to know is what came to the left, above, and to the top left of that. Sorry, my words are getting messed up, but to the top left of that. We can see that nothing is in those directions, so that's why we can solve this problem populating it from the top left. we will start here. We'll see that it's a 0. So what we're going to fill in here is 0. But even if it wasn't, if this was a 1, we would look to the left, above, and to the top left, but we'd see that we're out of bounds in all of those directions. So an elegant way to solve this problem, if you are filling in a grid, like a matrix, you could create a grid that is not the same dimensions as the input, but actually has one more layer. And you could fill that in with all zeros. And then you'd fill in these positions. So that's a perfectly valid way of doing this. You just have to offset the indexes by 1. So if you're at like I, j in the matrix, you would be populating I plus 1 and j plus 1 in our own matrix. I'm going to handle this slightly differently in Python because I know some tips and tricks that make it a little bit easier. And if you want to learn those tricks, I have a Python for coding interviews course that you can check out on Leetcode.io. So to populate this, we see that this is a 0. Okay, put a 0 here. We go here, it's a 1. So we look above, left, and there. We're out of bounds in all those these directions. So we're going to get a minimum of 0 from those 3 directions. And we're going to add that to 1. So we say the biggest square we can create, where this guy's the bottom right of the matrix, is a 1. And we can keep filling these in. We'll get 1 here, and I think a 1 here. And this is where things get a bit more interesting. We look here, here, here. The minimum of those, unfortunately, is still 1. So we say the biggest matrix we can create, where this is the bottom right, is 1. We can't do a 2 by 2. Now we get here. This time, the minimum of these is 1, so we can create a 2 by 2. And this guy also, we can do a 2 by 2. And now I realize I created a 4 by 4 matrix when we actually have a 3 by 4. So please ignore this bottom row. I really apologize. I think it's because this looks like a square, like the shape of it is like a square, even though like there's 3 rows, but 4 columns anyways. Filling in the rest of these though, you'll get a 0 here. From here, you'll get a 1. From here, we will get a 2. And from here, we will get a 3. So you solve this problem after this by just summing up all of these, but you could also sum them up as you go. And I believe the total is 15. Now, you might have noticed that a small optimization that we can make is if we have a row, like look at any particular value. If we're populating this guy, all we really need is the one that's above, to the top left, and to the left. So actually, we can do this with 2 rows. We only need 2 rows in memory at a time. So first, I'm going to start with the less memory optimized approach. I'm going to declare DP. Normally, we would make this a matrix, like a 2-dimensional matrix, but it's easier in Python to use a default dictionary where the default value is int, because now if we do something like this, let's say DP of 0 and like -1, we would know that this is technically out of bounds. If we were doing something like this, a DP of 0, -1, or maybe both of these are -1, that'd be out of bounds. But with a default dictionary, it'll return a default value of 0 if this key has not been inserted into that dictionary. And a dictionary is like a hash map in Python. So now, knowing that, we're going to declare our result. That's going to be the total that we've counted so far. That's what we're going to return. And now we're going to populate that grid sort of from top left to the bottom right. So for row in range that, and column in range that. If the value at this coordinate is a 0, we want to skip it. In other words, only if that value is a 1 do we actually want to do something. What we want to do is say DP here at row column is going to be 1 because we know that it's a 1 in that position. So it's at least going to be of size 1 plus the minimum of the 3 subproblems. And this time the subproblem is not going to be like this. It's not going to be row plus 1 column. We're actually going in the other direction. We're going to look above, to the left, and to the top left. So we're going to make this a minus. I'll copy that and paste it a couple times. Here we will do column -1, and here we'll also do column -1 and row -1. So the good thing about Python is we can take the minimum of 3 values at a time. So this is good. And then once we're done populating that, we should probably also add it to the result just to keep track of it. And that is the entire bottom-up solution. I'll run it. You can see that it works and it's very efficient, but we can optimize the memory So I'm going to assume now that this is not like a two-dimensional array, it's like a one-dimensional array. So we're going to assume that that's like the previous row. The previous row is going to be all zeros. So that's consistent with how a default dictionary is going to behave. And what we want to do for each row is compute the current row. Let's say current DP, and that's also going to be a default dictionary. And I'm going to treat it like a one-dimensional array that we can't get an index out of bounds error with. So I want to populate this. So I'm going to change this to current DP. We don't need the row anymore because we're assuming this is a one-dimensional array. And so we just need the column now. So to populate this value, we need what came above it. So this is now going to be a DP of just the column because that is the row above. The value, let's say to the left, is going to be current DP at column -1. And this is above and to the left. So that's just going to be DP of C -1. So I'll just do that and there. And to the result, we want to add this value. So not too many changes really to make this more memory optimized. The only thing is here, after we're done populating a row, let's set it to be the previous row. So DP should be current DP at this point. So now let's run this. And you can see this solution also works, and the memory is definitely more efficient. Leetcode just doesn't always indicate that. If you found this helpful, check out Leetcode.io for a lot more. Here's that Python for coding interviews course I was talking about. Pretty soon I'm going to be adding like an OOP course. And I recently added a SQL course where you will actually learn Postgres via a bunch of interactive lessons, and they're actually very high quality. Each of them has like a mini lesson, and then they ask you to solve like a pretty small challenge. So rather than just watching videos and reading, you actually have to write code, and that's really the best way to learn. And I think this course makes it very easy for you and formats everything that you need in one easy place.